So trying to prove if this is a biconditional statement or not, using the dog example. If it is a dog, then it is a mammal. True or not true? If it is a dog, then it's a mammal. True. Reverse it. If it's a mammal, then it's a dog. Is that true? No. So a dog is a mammal is a bad definition for a dog, right? It's not specific enough. Okay? So using biconditionals, we can come up with real solid pieces of statements as evidence in building these arguments, okay? And again, a biconditional, we don't start with if and then. We actually we use the if and only if phrase in between. So if a number is 4, then it equals 2 plus 2. That's the conditional. If its converse is true, so when you reverse it, if it's true, then you can write it as a biconditional. The biconditional does not start with if, okay? It starts with the conclusion or hypothesis and ends with the other one. A biconditional, here we go. A number is 4 if and only if it equals 2 plus 2. It is Mr. Davidson's room if and only if it's room 202. So you take the conditional, you check its reversibility. If it's reversible, then you can write it as a biconditional. Biconditionals make for good definitions, and it's more of a solid piece, more of a solid statement that you can use as a piece of evidence. A perm will lose its curl if and only if it gets wet. You will lose your perm if and only if you take a shower right afterwards. Pretty solid statements that Elle Woods used to get her friend off of trial there. By the way, I don't think a lot of trials are that way. That was pretty dramatic. But maybe they are. All right, ready to move on here? No? Okay. Yeah, Chutney really kind of threw herself under the bus there. She didn't admit to it.
I thought it was her.
Yeah, if she didn't admit to it, she still could have had some plausible deniability. Although the jury would have had a lot of reasons to find Miss Wyndham innocent, because the eyewitness testimony was false. But I don't know if Chutney would have got arrested right away. I don't know. I mean, they would have had more questions for her, but she wouldn't have got arrested on the spot. I can guarantee that. So, okay, I'm moving on here. I'm going to give you 4 sentences. We have to determine whether or not they're a good definition, and they're a good definition if they are reversible. Okay?
Do we have to write them down?
No, good question. Yeah, I just want you guys to pay real close attention here, okay? All right. It's a good definition. This is a good definition of a fish if it's reversible, okay? A fish is an animal that swims. Reverse it. If it swims, then it's a fish. That's not a good definition, right? Can you swim?
Yeah.
Are you a fish?
Yeah. Fish.
A dolphin swims, right, day and night? They're not a fish. They're a mammal. Whales, mammal. They're not a fish. Okay? So that is not a good definition. It's not reversible.
I think so.
Rectangles have 4 corners.
4 corners have rectangles.
If it has four corners, then it is a rectangle. Now, a square is a rectangle. A square is a real specific type of rectangle. Okay? But what do we... Thank you. What do we know about rectangles? Four sides, four corners, right? But what do we know about those corners specifically? Yeah, they have 90 degrees. So you can draw a shape that has four corners that maybe isn't 90 degrees. Okay? Isn't a rectangle. That's not a rectangle, right? But it's got one corner, 2, 3, 4. Okay? It's still a quadrilateral, but it's not a rectangle. So that one is also not a good definition. Giraffes are animals with very long necks. If an animal has a very long neck, then it's a giraffe. There you go. Yeah, so dinosaurs would be a good counterexample, right? Like the, what are they called? Brachiosaurus. Yes, thank you.
What?
I gotta be honest with you, I acted like I didn't know that. But I knew it the whole time. I'm kind of a dinophile. What about a brontosaurus? Yeah, man. Now brontosaurus they think is just a baby version of a brachiosaurus. Is what they tell me. So those are good counterexamples. That one's incorrect. A penny is a coin worth 1 cent. A coin worth 1 cent is a penny. Sounds good to me. I mean, you could maybe make an argument like, well, this coin is from like Brazil and it's worth 1 cent, but that's a stretch. Okay, I'd say that's a good definition of a penny. I don't know how else you define it. So that was good. So you could write this as an if and only if statement. Since it's a good definition, it would make for a good biconditional. So it would look something like this. A coin is a penny if and only if, see I use the IFF there? That stands for if and only if, that's shorthand. If and only if it's worth 1 cent. A coin is a penny if and only if it's worth 1 cent. A coin is worth 1 cent if and only if it's a penny. You can reverse that around. All right, any questions? All right, answer this then. How do you know it's a good definition?
If you can flip it around.
It's reversible if you can flip it around. Good. How do you know if it's biconditional? No, it is. Yeah, if it's reversible, right? If it's still true whenever you flip it, if it's reversible. So a good definition and a biconditional, they go hand in hand. All right? All right, here's our assignment. You can put that on a doc in a document, or write it out on paper, either one. Let's get it ready. Yes, share that with me. Yeah, that's fine. Yeah. All right. We getting this ready? So we're doing evens here. We'll start with 2. So number 2, how can you combine the following statements as a biconditional? Biconditionals use the phrase if and only if. So you don't start the phrase with an if. You take the P and you take the Q and combine them with an if and only if phrase in between, okay? Alright, so the statements. If this month is June, then next month is July. If next month is July, then this month is June. Sounds good, like it's reversible, right? If this month is June, then next month is July. If next month is July, then this month is June.
True.
Okay, sounds good, right? But it's not a true or false question. We need to write it. We need to combine the sentences as a biconditional statement. So we're going to combine these using an if and only if phrase. Don't start with if. What do you think? We're using the if and only if phrase. Kinsey? Beautiful. Well done. She said, this month is June. If and only if next month is July. So again, start here without the if. Whoop. This month is June. If and only if next month is July. And you could do that the other way around. Okay, next month is July, if and only if this month is June. And feel free to use that shorthand IFF. Number 4. Explain how the term biconditional is fitting for a statement composed of two conditionals. Why is biconditional fitting for a statement composed of two conditionals? Why is bicycle fitting term for a vehicle that has two wheels? Because bi means two. Yep. Because bi means two. Did you catch that? Any repeats there? Yep. The prefix bi means two. Number 6. Which of the following statements is a better definition of a linear pair? A linear pair is a pair of supplementary angles. So if it's a good definition, I should be able to reverse that. Supplementary angles are a linear pair. First off, let's try to remember what a linear pair is. A linear pair are angles, they're together, they are adjacent, they're next to each other, and they form a line, right? A linear pair forms a line that's 180 degree angles. What are supplementary angles? Yeah, any two angles. They don't have to be next to each other. Any two angles that add up to 180 degrees. Any two angles, okay? So, a pair of supplementary angles is a linear pair. Is that reversible? It's not, because supplementary angles don't have to be adjacent, okay? Supplementary angles don't have to be right next to each other. They don't have to share a side, okay? So the first one's not a good definition. The second one, let's read it. A linear pair is a pair of adjacent angles. There's the key word. Linear pairs have to be adjacent with non-common sides that form opposite rays. So their non-common sides form a line. Or opposite rays. So A is a better, or not a better, but a good, is the definition, actually, of a linear pair. Why? Why is that the better definition of a linear pair? This is going to be your answer for any time they ask, why is this a good definition? Because it's reversible. Why is it a good definition? Because it's reversible. So that one's the better one. All right, number 8. So each conditional statement below is true, right? It's converse. What's converse mean? Reverse. Converse means reverse. Right? It's converse. If the converse is also true, combine the statements as a biconditional. So we're going to write an if-then, a converse that would reverse it, and then a biconditional would be a statement that doesn't use if and then, but it uses if and only if phrase in between. Okay. So number 8, the first is true. We need to write it. Write its converse. Someone raise their hand and tell me what the converse is going to look like there. Converse on number 8. What will it look like? Go ahead, Kenzie. Good. You would take the hypothesis, the converse means reverse, so the 2x minus 5 equals 19, that would come first. So if 2x minus 5 equals 19, then x equals 12. Is that true? I'm doing some of this in my head. If I add over 5, that would be 24, then divide by 2, that would be 12, right? That'd be true. So to write it as a biconditional, I use the phrase if and only if, and I can use shorthand there, the IFF. So the biconditional would be x equals 12 if and only if 2x minus 5 equals 19. What? Okay, number 10. If x equals 3, then the absolute value of x equals 3. Reverse it. If absolute value of x equals 3, then x equals 3. Is that true or false? Kenzie, you're shaking your head no. Why do you think Kenzie's shaking her head no? Are you thinking the same thing? Why is this no? Why is this false? Counterexample. I'm looking for a counterexample. X could equal 3, but what else could x equal? Not if the absolute value of x equals 3. Negative 3. Yeah, good. So negative 3 would be a counterexample here. That one's false. If the absolute value of x equals 3, then x equals 3. Or it could also equal negative 3, which is not mentioned here. So that one's false. Since it's false, let's provide a counterexample. And we don't need to write it as a biconditional. We can't write it as a biconditional. Number 12, if P, then Q is true, then not Q, then not P is true. So the first is a conditional. This right here, it's a little confusing. This right here is the symbols we use for a conditional statement, right? So if that's true, then not Q, then not P is true. This is what we use for the contrapositive. Do you remember how those, did they share the same truth value or were they different? The conditional and the contrapositive. Conditional was your original statement, and then the contrapositive is where you did both the converse and the inverse. So you had the original statement, and then you had where you switched the order and you negated. So if one is true, is the other true? Do you guys remember? No one remembers. See a lot of people shake their head. Okay, conditionals and contrapositive, they hold the exact same truth value. So if one is true, the other one is true. So this can be written as a biconditional. Let's first reverse it. So if P then, or if not P then not Q. Set it backwards. If not Q then not P. Then if P then Q. And then we also have to write that as a biconditional. So continuing on here. If P then Q. If and only if not Q, then not P. That one's confusing, but those are symbols that we use for conditional and contrapositive. All right, any questions before the bell rings? All right, I want to give you guys time to find your notebooks and to turn in your notebooks.